Hello guys, my name is Felix from examsconnect.com and welcome to our class Vectors. It is a continuation of measurement and we are almost winding up. In fact, this is the last part of measurement, and we first define what is a vector. But before that, how do we differentiate between vectors and scalar quantities? So a vector quantity, it is a quantity that has both magnitude and a specific direction. It is a quantity that has both magnitude and a specific direction. And when you talk of magnitude, you are talking of the measure. You can quantify it as a figure, maybe a decimal or a whole number. You can quantify it. That's what we talk when we're talking of magnitude. Now, next we have other quantities that are known as scalar quantities or scalar quantities. Now, for the case of scalar quantities just have magnitude but no specific direction. Magnitude but no specific direction. Some of the quantities that we have in measurement can either be vectors or scalars, or even scalars, as you will call it, scalars or scalars. And that's the difference between a vector quantity and a scalar quantity. A vector quantity has both magnitude and direction, whereas a scalar quantity just has the magnitude part. And when you talk of magnitude, remember we are talking of the measure. It has a measure, a quantity, a measure that you can give in terms of a figure. Next we have some other examples. Scalar. So I'm going to have scalar there. Then we can have vectors on the other side. Examples of scalar quantity, we have time. Time, 30 seconds, 20 seconds, 20 minutes, 4 days. When you're talking of time, you can give it a span, a magnitude, but you cannot give it a direction. For example, you cannot talk of 40 minutes west or 40 minutes this side, the left side. It doesn't really make sense, especially in physics. Next, we have another example of a scalar quantity. We have distance. Distance. So somebody can give you a distance. For example, you can be given a distance like 20 meters. When somebody tells you measure 20 meters, we need to be specific. Where do you start from? But because that's a distance, we don't have the direction. Next, we have another example, power. Power. That's measured in terms of watts. And power does not have a specific direction and to which it moves to. Next, we have mass. Mass. Mass is the amount of matter that is contained in a substance. The mass that you have in your body, the mass that any object has or any matter has, cannot be given in a direction, but you can just quantify it. That is in terms of kgs, pounds, or newtons. In the side of vectors, we can give examples of vectors. For example, I can give an example, velocity. Velocity. Velocity has a direction because you need to be showing whether it's moving forward, backwards, top, left, and we use negative values, negative or positive values in case there's a change in the direction of the velocity. Next, we have displacement. Displacement is a type of a distance, but with a specific direction. We have displacement. Next, we have current. These are just random examples. Now, for the case of currents, current moves in a specific direction, and apart from that, we can measure current using ampere. It was among the standard units that we listed when we were beginning. Next, we have weight. As we compare it with mass, weight is a bit different because weight is a push or a pull. And in fact, it is the pull, the gravitational pull that is gotten by anybody or matter by the earth. Gravity gives us our weight. The gravity gives you the weight. So because there's a pull, the direction of the pull makes it to become a vector quantity. So those are just examples of vectors and scalar quantities. There are so many. We are just giving examples that can be that you can relate to, so that you can differentiate between scalar and vector quantities. Now, I want to give an example involving the vectors. Consider a push that is on that direction. That's a push that is on that direction. Maybe I call it F. F, it is a force that is applying on that direction. Now, when you're pushing an object diagonally, that does not stop the object from experiencing a left or a vertical. It can experience a horizontal or a vertical movement. In fact, a diagonal movement is a combination of two movements, the horizontal and also the vertical movement. Therefore, if I call this FH and this one FV, we can say that FH is equals to F cos theta degrees, where theta degrees is the amount of degree. It is the displacement that is in between the diagonal push and the horizontal push. So if you want to consider how much force is being experienced horizontally if you push a body diagonally, then you can have it as FH is equals to F cos theta, where F is this diagonal push. What about F vertical, or is this upwards motion? How much force is experienced by a body that is pushed diagonally? How much force does that body experience vertically? Because if you are pushing a table diagonally, there must be a component that is causing it to move vertically. Therefore, FV will be defined as F sine theta, where this F again corresponds with our diagonal force. So this is a bit different from what we have in the Pythagoras theorem. It's a bit different because now we are working with angles. For example, if this was the case of a Pythagoras theorem, then we can say that the horizontal part, maybe 5 units, corresponds with 4 units horizontally and 3 units vertically. This is different from what you are working out here. In the case, however, as much as these are vectors, we can work them this way, or we can use the angle displaced at the middle of the two vertical or the horizontal parts. So this one is also a kind of a vector, where the vector that has 5 units is a component of 3 units, 1, 2, 3, and 1, 2, 3, 4. Both of them arrives at this terminal point. So Pythagoras theorem can also be applied to get a vector unit. However, in case the units are not given, we can use the angle. That's the trigonometry. That's a bit of mathematics, but you borrow it from it, where if FH represents the diagonal push, then we can get the horizontal push as FH, which is F cos of theta, or the vertical push as FV is equals to F sine of theta. With that, we can try an example involving vectors. Remember that this is the final part of measurement. However, it is also good to understand the vectors because, as we have seen, different measures are in different positions. They are scalars and also have the vectors. So in the example, calculate the vertical component of the following. Calculate the vertical component of the following. And this is what we are given. A push was made diagonally. and the push was 10 newtons, and the angle between that and this ground is 50 degrees. However, you are being asked for the horizontal component. This is what you are being asked for. The horizontal, So this was 10 newtons. The diagonal force was 10 newtons. The angle between the surface and the diagonal force is 50 degrees, but you're being asked for the vertical component of that force. So how do we calculate that? We can calculate it this way. By saying solution F vertical is equals to F sine of theta. F vertical is equals to F sine of theta, where F stands for the original diagonal push. So therefore we have this as 10 sine 50. The 50 degree is the displacement that the diagonal push is having from the ground. So we have this as F vertical is equals to 7.66 newtons. F vertical, force that is applied vertically is 7.66 newtons. Another example involving the same. Calculate the horizontal component. Calculate the horizontal component in the following setup. We have this as a diagonal push of 20 newtons, and the relative angle between the ground and the push is 35 newtons. And then you ask how much force will be experienced horizontally on the surface. Horizontally, then we have this as the solution, that FH is equals to F cos of theta. FH is equals to F cos of theta. So we have this as, where F is this original diagonal push of 20 newtons. So this will be 20 newtons cos 35 degrees. That gives us 20 cos 35. That gives us 16.38 newtons. 16.38 newtons. That will be the force that is experienced horizontally on the surface, which is on the ground. Next, we want to look at, what about the components of vectors? Components of vectors. We want to look at components of vectors. We want to consider what happens when two forces, remember a force is a vector, pushing on the same object. Sample A. Let us start with the first sample, sample 1. This is a body that is at the center of two forces. One force is pushing at 3 newtons. We have 3 newtons pushing it to the right and 5 newtons pushing it to the left. Therefore, at the end, we want to see where will the body move and by how many newtons. So we can consider, since we know that force is a type of a vector quantity, we can consider it moving to the left as positive and moving to the right as negative. Therefore, we have this as positive 5 newtons added to negative 3 newtons, and we have it as 5 newtons minus 3 newtons, giving us 2 newtons. And since it is a positive, we can conclude that the body will move to the right, to the left, so that we can have it as 2 newtons towards that side. So that's the advantage of using vectors in your solution, because we can define a direction using a sign, so that we can have the left being positive and the right being negative. However, that does not mean that you cannot interchange the values. You can, so that you can have this as positive, whereas this is negative. However, at the end, the direction will be determined by the sign that appears. So that if it is a positive, then we can define the movement as being to the left. And that's how you look at the components of a vector. Some vectors can also cancel out. For example, number 2, 3 newtons acting against 3 newtons. We can now have it this way, to the right being positive and to the left being negative, so that we can have the component as a sum of 3 newtons, positive 3 newtons minus 3 newtons, giving us 0. Therefore, there won't be any resultant force at the end of these two motions. So the body will remain stationary. So with that, that's the end of the topic on vectors.